Hello, am I audible to everyone?
Sir.
Yes, sir.
And the slides are also visible?
Yes.
Okay, thank you. So let us start with what we have started in the last class. In the last class, we started looking at the directional nature of the thermal radiation, isn't it? And why directional nature of the thermal radiation is important, because when we are looking at the net radiative heat transfer between two bodies, how much is the solid angle subtended by one body on the other, that is important, isn't it? Because only the radiations passing through that solid angle will be intercepted by another body. And that is why when we are looking at the net radiative heat transfer, this word is net radiative heat transfer is very important. Net radiative heat transfer means the net radiative heat transfer between these two bodies that depends on the solid angle subtended by one body on the other. Okay. So that is why we started looking at the concept of this solid angle. We said that the solid angle is nothing but what? It is nothing but the area we find out at the radius r equals to 1, isn't it? So in general, that is nothing but area divided by r square, isn't it? And it is denoted by steradian, isn't it? Then again, we have looked at we have considered a point uh, differential area dA1 and the area A2. Why we have kept a differential area dA1? Because then we will be integrating it over the complete area. And since in this case, depending on what area I am going to have here, dA1, based on that my solid angle is going to be varying, isn't it? So that variation is captured by taking a elemental differential area here, and then it will be integrated over the complete area. Okay, that is the reason why we have started with the differential area dA1 here. Again, this differential area dA1 is going to emit the radiation in the entire hemispherical region, and only part of that will be intercepted by A2. Okay. So based on this, again, then we started looking at the derivation of this, and also the concept of radiation intensity we have brought in. So radiation intensity, we said radiation intensity is nothing but the radiant flux passing in the specified direction per unit solid angle, isn't it? So this mathematically, this can be defined as IB lambda is nothing but the spectral radiation intensity of a black body, that can be given as d EB lambda by d omega. So here EB lambda is nothing but spectral emissive power of a black body, whereas omega is nothing but the solid angle. So from this equation, we can rearrange everything and we can find out the EB lambda. So EB lambda can be obtained as integral IB lambda d omega. So if we integrate the spectral radiation intensity over the solid angle, that gives us the emissive power of a spectral emissive power of a black body. Again, whether we are integrating over the hemispherical region or the complete spherical region, based on that we can define this as a hemispherical spectral emissive power or a total or a emissive power, just emissive power. So in this case, since we are integrating it over the hemispherical region, that's why we are calling this EB lambda as a spectral emissive power, hemispherical spectral emissive power we are calling it, isn't it? So now we have put everything here. So in this case, you can see that this phi is varying between 0 to 2 pi, whereas this psi is varying between 0 to pi by 2, and based on that we have put it here, the limits we have put. And since this phi in this entire equation, there is no phi term, so this phi we can separate it out. So this d phi integrated over 0 to 2 pi is going to give me directly 2 pi. So that this 2 pi is coming out based on that. Again, this spectral intensity of a black body can be represented in terms of a the spectral intensity in a normal direction. So this spectral intensity of the normal direction, in the normal direction, if it is present, its component along this solid angle we can obtain as IB lambda. So IB lambda can be obtained as INB lambda cos psi, and that we can put it in this equation. So ultimately, if we integrate this entire equation, what we get is pi into INB lambda. So this equation gives us the information that the spectral emissive, the hemispherical spectral emissive power of a black body is pi times the spectral radiation intensity in a normal direction. That's what we have obtained here. Now this entire equation we can further integrate over the wavelength. Since wavelengths are varying between 0 to infinity, we can integrate it over the wavelength, and after integrating, what we get is hemispherical emissive power of a black body, that is nothing but pi times radiation intensity of a black body in a normal direction. So INB here, subscript lambda we have omitted in both EB as well as INB. So after this, what we have started looking at, so far we have only started looking at the hemispherical region, but when we are concentrating on finding the net radiative heat transfer, so we will have a situation like this. There are two differential areas, DA1 and DA2. Why we have taken a differential areas? Because these we are going to integrate over the complete area, isn't it? Later on. So DA1 and DA2, these are making an angle of beta 1 and beta 2 with a normal direction, and we are interested in finding out the net radiative heat transfer between these two. Okay, that's what we are interested in. Now in this case, the radiation emitted by DA1, the fraction of the radiation emitted by DA1, which will be intercepted by DA2, depends on the solid angle subtended by DA2 at DA1. Okay, so this solid angle we can obtain as DA2 cos beta 2 L square, isn't it? DA2 cos beta 2 L square, that will be the solid angle subtended by A2 at DA1. Similarly, the radiation intensity in the normal direction we know, IN we know, but we can find out what will be the radiation intensity in the direction of A2. So that can be obtained as IN cos beta 1, isn't it? And IN we can represent in terms of the emissive power. So that is nothing but EB by pi from the previous calculation, isn't it? EB by pi is nothing but INB, isn't it? So EB we can again replace by sigma into T raised to the power 4 by pi cos beta 1. And if you put this intensity and the solid angle in this equation, so the rate at which radiation emitted by DA1 flowing towards the DA2 can be obtained as intensity IB into solid angle d omega into the corresponding area of this surface DA1. Okay, so after putting everything, what we get is cos beta 1 cos beta 2 DA2 by pi L square sigma T1 raised to power 4 into DA1, and this bracket term we have represented as dF12. Here dF12 is nothing but the shape factor of surface 1 with respect to surface 2. So it is nothing but the fraction of a radiant heat flow rate from DA1 which will be intercepted by DA2. Okay, again we have kept here in a differential form because we are doing all these calculations for a differential surface area. That's why this shape factor also represented in a differential form. So same thing we have extended for a surface 2 also, and we have obtained the equation as dF21 sigma into T2 raised to the power 4 DA2, and we said dF21 is nothing but a shape factor of surface 2 with respect to 1. Now if we subtract both these radiative heat transfers, isn't it? So this is nothing but the radiation intercepted by radiation emitted by surface A1, which will be intercepted by A2, and similarly we have obtained the radiation emitted by surface 2, which will be intercepted by A1. And if you subtract both these factors, what we are going to get is dq12. This is nothing but the net radiative heat transfer between surface 1 and surface 2. So you can see that in both these equation, this bracket term is, see this dA1 and dA2, if I put it here, this entire bracket term cos beta 1 cos beta 2 dA1 dA2 divided by pi L square, this term is a constant term. This is common term in both the fractions. So this I can take it out, including this sigma. Then the remaining will be T1 raised to power 4 minus T2 raised to power 4. So this equation can be represented as dF12 sigma T1 raised to power 4 minus T2 raised to power 4 dA1, and it is also can be represented as dF21 sigma T1 raised to power 4 T2 raised to power 4 dA2. So from this equation 8 we can say that dF12 dA1 is same as dF21 into dA2. So this is a reciprocal relation which is valid. Okay. Since everywhere we are doing the calculation only for a differential surface area, we started with two differential surface area A1 and A2, dA1 and dA2. And as I said that to get the complete picture, we have to integrate it over the total surface area dA1, A1 and A2. So that's why we are integrating this dQ12 over the surface area A1 and A2. So only this particular shape factor term is going to get integrated. Sigma T1 raised to power 4 minus T2 raised to power 4. This will remain, constant. So this we have taken out. So after integration, this bracket term is represented as F12A1 or F21A2. Isn't it? So F12 is defined as 1 by A1, this entire bracket term. Similarly, F21 is defined as this entire bracket term divided by A2. Okay. So again, another interesting point to note down here is if any one of the area is very small, in that case, integration over that area is not required. For instance, in this case, if we assume that A1 is very small, in that case, we don't require integration over A1. And we can simplify this equation as Q12, this integration of this term only takes place over A2 and A1 we can take it common here. Okay, again we can represent this entire equation in terms of similar to equation 10, except that the definition of F12 and F21 will be slightly different. That's it. So up to this we have seen in the last class. Is it clear to everyone? At least the context is clear. We started, so see, when we started the radiation, we have looked at different laws which are given by the researchers. Then we said that how much the energy will be radiated from the individual surfaces. That's what we have said. But we have not talked about what will be the net radiation between two surfaces. When we are talking about the net radiation between two surfaces, in that case, additionally, the shape factor comes into the picture, and this shape factor is basically is what it is. It takes into account the solid angle, isn't it? You can see these are the terms because of the solid angle, isn't it? Correct. So how much is the radiation intercepted by one surface? How much the radiation emitted from one surface is intercepted by another surface? That fraction is represented by a shape factor. Is it clear to everyone? Context is clear?
Yes, sir.
Your S is not having that confidence. Is it clear?
Yes, sir, it is clear.
Achha. So up to this we have seen in the last class. Okay. So now let's look at some of the rules with respect to this shape factor. These rules are very important. So very often, when we are looking at the real life radiation heat transfer, our surfaces are not, flat or something, isn't it? Different geometries are there, isn't it? So shape factors could be very complex in those cases. But if we use this shape factor algebra or the rules with respect to this shape factor, component factor or a view factor, then our analysis becomes very simple. Okay, so that's why we are looking at different rules with respect to these shape factors. So the first rule in the shape factor algebra is shape factor F12 and F21 between two surfaces 1 and 2 are related by reciprocal relation. They're very important. F12A1 is equals to F21A2. Remember what is F12? F12 is nothing but the shape factor of surface 1 with respect to 2. What is practically it means? It means the practically whatever the radiations are emitted by surface 1, what is the fraction of those radiation which will be intercepted by A2? This is given by F12. So this reciprocal relationship is always true when we are looking at the radiation between two surfaces. F12A1 is equals to F21A2. That is what we have seen here, isn't it? You can see F12A1 is same as F21A2. Can you see the point? Is it clear?
Yes, sir.
Now, this reciprocal relation sometimes becomes simplified. Whenever one of the surface is completely encompassing the another surface, it's completely surrounding the another surface. In that case, the shape factor corresponding to that particular surface becomes 1, isn't it? Do you agree? For instance, let's say in this case, let's say a surface 2 is completely surrounding surface 1, and surface 1 is convex. What will happen? All the radiation emitted by surface 1 will be intercepted by surface 2. Do you agree? So what will be the value of the fraction? Remember, F is a fraction, isn't it? So what will be the value of the fraction? It will be 1, isn't it? Do you agree?
Can you repeat the last one?
I'll repeat. Okay. Just a minute. Let me just put this. So small details are there, but if you pay the attention, things will be clear. So what we are trying to say here is let's say I am having a surface. This is, let's say, surface A1. Okay, this is A1. And this A1 is, let's say, put it in a rectangular box like this. Okay, so this is 1 and this box is 2. So what will happen to F12? What is F12? F12 is nothing but the shape factor of surface 1 with respect to 2. That means the radiation emitted by surface 1, what is the fraction of that will be intercepted by 2, isn't it? So in this case, what will be F12? All the radiation emitted by this surface 1 will be intercepted by 2, isn't it? Do you agree?
Yes, sir.
So in that case, this F12 will be what? Just 1. So this equation can be further simplified as A1 F21 A2. So you can obtain F21, which is nothing but the F21 is what? F21 is nothing but the radiation emitted by what is the fraction of radiation emitted by surface 2 intercepted by 1, isn't it? So that can be obtained directly as A1 by A2. So can you see? You can obtain F21 easily if you know this condition is true. Does it make sense to everyone? Hello?
First, since they are enclosed in a box, then won't all the radiations from 2 also be absorbed by 1?
No. Not necessary. Not necessary. This box is going to emit the radiation outside also here, isn't it? And
But it was
Also, the radiation emitted by this box from surface here may be intercepted by this surface here, isn't it? Correct?
Okay.
So it need not be intercepted by this only, isn't it? Need not be intercepted by this surface one only. Okay. So in fact, that part also we will see in these rules. Okay. So now let's move to the second rule. What is the second rule? The value of the shape factor depends only on the geometry. This is very important. The value of the shape factor depends only on the geometry. This only word is very important. Only on the geometry and orientation of the two surfaces and the orientation of the two surfaces. Because of this fact, once the shape factor between the two surfaces is known, it can be used for calculating the radiant heat exchange between these surfaces at any temperature. So it doesn't matter what temperature both these bodies are having. If I wanted to calculate the net radiative heat transfer between these, if I know the geometries and the orientation, and if I know the temperature of both these bodies, then I can easily calculate it. That's what it is saying. Clear? So these shape factors are independent of temperature, wavelength, any other variables. It is only dependent on geometry and orientation of the two surfaces. Does it make sense to everyone? Hello? The third rule is a surface has a shape factor with respect to itself. This is very important. So the example which I was giving here, so radiation from here may be intercepted here. So that means what? The surface 2 is having the shape factor with respect to itself. That can happen for these surfaces also. For instance, if I'm having a radiation emitting from this surface, this will be intercepted here, isn't it? So if I'm having the concave surface like this, in that case, the radiation coming off from one part of the surface can be intercepted by another part of the same surface. And therefore, a surface can have a shape factor with respect to itself. Do you agree? Does it make sense to everyone?
Yes.
But if I'm saying that, but even this rule, is implemented only if the surface is concave. But if I'm having the surface which is flat like this or a convex like this, in that case, no way it is possible that the radiation emitted from these surfaces will be intercepted by the same surface itself. Is it? Yes or no? So when we are having a flat surfaces or a convex surface like this, this is the convex surface, isn't it? Then my shape factor of the surface with respect to itself is 0. Do you all agree with me? Hello? Does it make sense to everyone what I'm saying?
Yes, sir.
Now let's make our life a little bit more complicated, isn't it? So very often in a practical cases, we don't look at only two surfaces. There could be n surfaces, and these n surfaces are enclosed. So we are having n surfaces make up an enclosure. So in this case, what will happen? Any one surface, any ith surface, if you select, the radiation emitted by this ith surface will be intercepted by all n-1 surfaces. Do you all agree with me? Yes or no? Correct? So for instance, okay, I try to make a figure for you so that you will appreciate the concept. Sorry. So let's say this is surface 1, this is 2, this is 3, this is 4, 5, 6, and this is 7. These are the 7 surfaces. If I consider any surface here, let's say any one, the radiation emitted from this surface will be intercepted by all the remaining n-1 surfaces. Do you all agree? Does it make sense? So that means what? That means what? What is shape factor? It is nothing but the fraction of radiation emitted by a particular surface, that what fraction of that will be intercepted by other surface, that is nothing but the shape factor. Okay, so if I calculate the shape factor of, let's say, surface 1 with respect to 2, surface 1 with respect to 3, surface 1 with respect to 4, 5, 6, 7, and itself, its summation should be equals to 1. Do you all agree? Isn't it? Correct?
Yes, sir.
Including itself. That's why we have used this, F11. F11 is nothing but the fraction of radiation emitted by 1, and it will be intercepted by 1 itself. Okay. So similarly, we can write down the expression for all n surfaces, isn't it? So this will be for surface 1, this is for 2, and this will be for nth surface, isn't it? Correct. So this is true only for the enclosure, but in addition to this additional equation 13, the reciprocal relation is always valid between two surfaces. So in addition to this equation 13, the equation 12 we have seen, that is going to be valid always. Okay, is it clear to everyone? Now, does it make sense to everyone what we are saying? Hello?
Yes, sir. Yes.
Okay, now last rule. Last rule is rule number 5. Rule number 5 is a very interesting rule. Okay, so see, consider that there is a surface area A1 and there is another surface area A2, but this surface area A2 is made up of two surfaces A3 and A4. So now in this case, if I look at F12, what is F12? F12 is nothing but the fraction of radiation emitted by 1 that will be intercepted by 2, isn't it? That is what nothing but F12. So F12 is given by this, F12 is given by summation of F13 and F14. So whatever the fraction of radiation emitted by whatever the radiation emitted by A1, the fraction of that will be obtained by the fraction of the radiation intercepted by A3 and fraction of the radiation intercepted by A4. That's why we are writing F12 as F13 plus F14. But the complications come when we are looking at the reciprocal relation. So what will be the reciprocal relation here? Reciprocal. So here what we are saying is the fraction of radiation emitted by 1 intercepted by 2. But let's say if we ask the reverse question, fraction of radiation emitted by 2 intercepted by 1. In that case, this reciprocal relation is not valid like this. You cannot write like this. This is not true. Okay, so this equation number 14 is correct. Equation number 14 is correct. And this equation number 14, we can apply the reciprocal relation for individual terms. So F12 will be given by what? F12 I can write down in terms of F21. So that is, remember, F12 into A1 will be given by what? F21 into A2, correct? So F21 will be what? F21 will be nothing but F12 divided by F12 A1 divided by A2. So that is what? So F12 will be given by F21 A2 divided by A1, isn't it? So that is what we have written here, this term, correct, from the reciprocal. Similarly, reciprocal relation we can apply for F13 also. So F13 will be reciprocal relation will be what? A3 divided by A1 F31. Similarly, A4 divided by A1 F41 for this. And if you simplify this, A1 will get cancelled out. So ultimately this equation is true. This is true instead of this. This is not true. This is not true. Is it clear to everyone? So fraction of radiation emitted by 1 which will be intercepted by 2 can be obtained by summing up the individual parts. But fraction of radiation emitted by 2 and intercepted by 1, we will not be able to obtain that just by simply adding the individual parts. Just by simply adding the individual parts. No. In that case, these areas also need to be multiplied. Is it clear? Does it make sense to everyone? Hello? Is it clear or not clear?
Clear. Clear, sir.
Achha, thank you. All right. Okay, so let's move to the next point. So maybe I just erase whatever I have written. Discard. Is my slides visible? Is my slides visible? Hello?
No, sir.
No. Okay. Let me share it. Just a minute. Okay, now it is visible. Is it visible now?
Yes, sir.
Okay, all right. So let's move. So now let's look at the, okay, so far we were talking about only two surfaces, isn't it? Only we were talking about the two surfaces, what will be the net radiative heat transfer. But let's look at if we are having an enclosure. A common, practical application is the furnace. So in the furnace, we will have a heat source. So the surface at which the heat is generated, there will be a heat sink where the heat is absorbed, isn't it? And in order to prevent the heat loss to the surrounding, we in general have a refractory valve. This refractory valve, what it does is, whatever the radiation are incident on this refractory valve, it is going to radiate, or it is going to whatever the radiation are incident on this wall, it is going to absorb that, and the same amount of radiation will be emitted by the refractory wall. Okay, so there are three surfaces: heat source 1, heat source heat sink 2, and refractory wall. So these three surfaces are, these are making a enclosure. So that's what is written. Consider a enclosure made up of three black surfaces. So all three surfaces are black. So surface 1 is at temperature T1. Surface 2, which is nothing but heat sink, is at temperature T2, and refractory material is at T3 to prevent the heat loss to the surrounding. So refractory material radiates energy at the same rate at which it receives the energy and attains the T3, which is between T1 and T2, which is natural, isn't it? So since it is whatever the energy it is receiving, the same it is, radiating. Now again, in addition to that, we are assuming that there is no convection taking place here. So radiation heat transfer is the sole, sole regime of the heat transfer. There is no conduction, there is no convection. So we are assuming that this entire space in between is filled by non-participating gas, or it's a vacuum is there. So there is no convection taking place. Is it clear? At least the system is clear to everyone. Hello?
Yes, sir. Clear.
System is clear. Okay. So here also we are, so far we are still considering the black surfaces. Okay. So all three surfaces we have assumed the black. Okay. But eventually we will see that from black surfaces we will move toward the gray surfaces. We will add some more complications later on. But for a time being, let's look at the black surfaces itself. So now in this case, the net radiation heat transfer from the surface 1, that is given as Q1. So net radiation heat transfer from Q1. Now radiation heat transfer from Q1 will be to what? It will be to surface 2 as well as surface 3, isn't it? So amount of heat radiated from surface 1 will go to either 2 and 3, isn't it? So I can write Q1 as Q12, Q13. Is it clear? Does it make sense? I can write Q1 is equal to Q12 and Q13, Q1 plus Q13. where Q12 is nothing but the net radiative heat transfer from surface 1 to surface 2, and Q13 is nothing but the net radiative heat transfer from surface 1 to surface 3. Is it clear? Does it
Yes,
make
sir.
sense?
Clear.
Now
Yes,
Q12,
sir.
how we can write down Q12? Q12 we can write down as A1 F12 EB1 minus EB2, isn't it? So here Q12 is nothing but what? Net radiative heat transfer. So net, when this word net is used, what it means? It is nothing but the difference between the radiation emitted by both these surfaces multiplied by a shape factor. Multiplied by a shape factor. Why shape factor? Because only the part of the radiation emitted by both these surfaces will be intercepted by another surface, isn't it? Correct? Does it make sense? So Q12 is given as A1 F12 EB1 minus EB2. Is it clear to everyone? Whether is it correct? Yes or no? So EB1 will be what? The total radiation coming from surface 1. EB2 will be what? Total radiation coming from surface 2. Difference between that and multiplied by a shape factor, because only the part of the radiation coming from B1 surface 1 and will be intercepted by surface 2, isn't it? So that's why this F12 will be added multiplied by A1. That's what we have calculated here. If you look at what we have calculated here, see, area 1 into F12, and this sigma into T1 raised to the power 4 is what? EB1. Sigma into T2 raised to the power 4 is what? EB2. Yes or no? Correct?
Yes, sir. Yes.
And similarly, we can write down the expression for Q13. Q13 can also be written as A1 F13 EB1 minus EB3. Since we are looking at the net radiative heat transfer between surface 1 and 3, so their emissive powers are, subtracted here. Okay, multiplied by a corresponding shape factor. Right? Now, since the net radiative heat transfer from surface 1, so surface 1 is radiating heat to both surface 2 as well as surface 3. So both these has to be added to get the net radiative heat transfer from surface 1. Do you all agree? Do you all agree with me if I write the equation like this? Equation 16. Hello? So this just I have put this Q12 and Q13 in this equation, isn't it? Right?
Yes, sir.
Okay. So now this EB1, EB2, this entire thing we have represented here. So similar to Q1, now in this case we have obtained the net radiative heat transfer from Q1. But similarly, I can write down the expression for net radiative heat transfer from Q2. Net radiative heat transfer from surface 2, that will be Q2. Similarly, I can write down the expression for net radiative heat transfer from surface 3, that will be Q3, isn't it? And the expression can be written like this. Q2 can be given as A2 F21 EB2 minus EB1 plus F23 EB2 minus EB3, isn't it? So this first factor will be the net radiative heat transfer from surface 1 to surface 1, surface 2 to surface 1, and this will be net radiative heat transfer from surface 2 to surface 3, and addition of those will be net radiative heat transfer from surface 2, isn't it? Correct? And corresponding shape factors are multiplied here. Does it make sense to everyone? I have just written a similar equation, that of equation this Q1 for Q2, but Q1 is the net radiative heat transfer from surface 1. So similarly, I am calculating net radiative heat transfer from surface 2 here. And also I am calculating net radiative heat transfer from surface 3. Isn't it? Is it clear to everyone now? These three expressions. Hello?
Yes, sir. Clear.
But in the problem statement, what we said, surface 1 is a source, so heat is generated at surface 1. Surface 2 is a sink, so it is absorbing the heat. That means the temperature of surface 1 will be higher than surface 2. Do you all agree? Correct? And regarding surface 3, what we are saying is surface 3, whatever the radiation incident on the surface 3, the same will be emitted by surface 3. So the net radiative heat transfer from the surface 3 is going to be what? Net radiative heat transfer from surface 3 will be what?
0.
It will be 0. Yes. So that's what we have put here. Net radiative heat transfer from surface 3 is 0. Now in both these equations for Q2 and Q1, there is unknown. So see, EB1 and EB2 is okay, but this EB3 is nothing but the emissive power of surface 3. So we are trying to find out what will be EB3 in terms of EB1 and EB2 from this equation by putting this 0. So by putting this 0, we can find out EB3 directly by rearranging the terms, isn't it? So EB3 is present here, EB3 is present here. We can collect those common terms and then rearrange everything. What we will get is EB3 comes out to be F31 EB1 plus F32 EB2 divided by F31 plus F32. So EB3 is what? EB3 is nothing but what? Emissive power of a surface 3. And this will be given by what? Sigma into T3 raised to the power 4. Yes or no? This will be represented as, this I can write down as sigma T3 raised to the power 4. Correct? So if I put it in this equation, I can calculate T3. So T3 comes out to be this entire thing divided by sigma and raised to the power 1 by 4. That will give me the T3. So T3 is nothing but the temperature of the refractory wall. This is the equilibrium temperature at which whatever the energy it is receiving from both surface 1 and surface 2, the same energy is radiated by the surface 3. Do you all agree with me? Hello? Do you all agree with me?
Yes, sir.
Now once I have obtained this EB3, now I can put this EB3 in this equation. I can put it here. I can put this EB3 here, isn't it? So once this part is 0, once this Q3 is 0, once this Q3 is 0, what it means? When and only 3 surfaces are there and all these 3 surfaces are enclosing each other. That means what? If Q3 is 0, that means Q1 should be equals to minus Q2. Correct? These are the only 3 surfaces are there. If I am saying the net radiative heat transfer by this wall is, this refractory wall is 0, that means whatever the Q is net radiative heat transfer from surface 1, that should be minus Q2. Do you all agree? There is no additional surface here. Only 3 surfaces are there, isn't it? So whatever the heat emitted by source 1, that will be taken by the source 2. Sink 2, isn't it? Do you all agree?
Yes, sir.
So that's what we have written here. Q1 equals to minus Q2. And this EB3 we have replaced by this new expression EB3 here, isn't it? That's what we have put it here. And after simplifying, what we get? So all these terms we can simplify. After simplifying this EB1 minus EB2, we can take it common. So after taking this as a common, EB1 minus EB2, we got this expression as Q1 equals to minus Q2 is given as EB1 minus EB2 in the bracket A1 F12 plus A1 F13 F32 divided by F31 plus F32. This is what we have obtained. In terms of temperature, this EB1 and EB2 we can represent in terms of temperature also. So that becomes sigma T1 raised to power 4 minus T2 raised to power 4, and this entire bracket remain as it is. So what does this tells us? What does this tells us? So when we are having such type of enclosed system, this particular factor represents what? This particular factor represents the overall shape factor. It represents the overall shape factor multiplied by area A1, isn't it? Do you all agree?
Yes, sir.
Isn't it? Now, okay, let's simplify. let's simplify this expression further, because here we are having F12 term, we are having F13 term, F32 term, F31 term, and F32 term. These are the different terms we are having. But we can represent this F13 term or F32 term or F31 term. All these F factors we can represent in terms of F12. We can represent like this. How? So let's apply the rules which we have seen earlier. So what if, remember, in this case there are three surfaces which are present in the enclosure, isn't it? And we are assuming that this wall is flat and this wall is also flat. So that means what? The shape factor of surface 1 with respect to itself is 0. Similarly, the shape factor of surface 2 with respect to itself will be 0. So we can write down this expression as, so F11 and F22, these are 0. So what we can write down? We can write down F12 plus F13 plus F11 should be equals to 1, but this F11 is already 0. So we can write down this as F12, F13 should be equals to 1. Similarly, F21, F23 plus F22 will be equals to 1, but F22 is already 0. So we can write down this F21 plus F23 equals to 1. Is it clear to everyone? Does it make sense? Remember, these are the same rules we are saying. This is the rule we are applying, rule number 4. In this case, there are three surfaces making up the enclosure. So we can write down this expression, isn't it? Do you all agree? Do you all agree with me?
Yes, sir.
Now, so see here F13 is there. So from this equation, this F13 here, this F13 here can be replaced by what? 1 minus F12. Correct? 1 minus F12 we can put it here. Yes or no? So this F13 I can represent in terms of F12 easily. Now let's look at F31 and F31. So F31 will be what? F31 again we can apply the reciprocal relation. So reciprocal relation in this case will be what? Okay, so I just do it here for you. So F13 will be directly given as F13 will be directly given as 1 minus F12, isn't it? So this is the first thing. So this F13 I can replace by this. Now let's look at F31. F31 will be what? So F31 should be equals to A1 F13, isn't it? So F31 will be given by A1 by A3 F13 and F13 we already know. So we can replace this also, isn't it? We can replace this by F31 can be replaced by A1 by A3 1 minus F12. Correct? Now the only last term is remaining, so F32. So F32 we have also done here. So F32 is given by what? F32. So from this equation, from this, what we are getting? F23 will be given by 1 minus F21. Isn't it? 1 minus F21. And F21 can be represented as F12. So that will be A1 by A2 F12. Isn't it? Correct? So F23 we have obtained, but we are interested in F32. So F32 will be given by what? A2 by A3, F23, and F23 we can put it from this equation, this. So that is what we have put here. So ultimately what we get is this F32 comes out to be this entire equation. Do you all agree? Does it make sense? Hello? Now put F13, F31 and F32 in this equation and simplify. After simplifying, you will get this equation. do this. I have already done it, but without wasting a time, this is what you should get after doing the entire thing. Is it clear to everyone? Hello? Does it make sense?
Yes, sir.
So it's not complicated. Just put these individual values in this expression. In this expression, if you put the individual values of F13, F31 and F32, ultimately this entire bracket is going to get simplified like this. Okay. Similarly, if you put this this T3 we have obtained here. Now in this T3, this F31 and F32, this F32, F31, all these terms, if you replace by F12, what you are going to get is this expression T3. Is it clear? Does it make sense to everyone? Hello?
Yes, sir.
Okay. So once we have obtained this, so Q1 in this case, when we are having a enclosure, you can see the complications we are now seeing. Maybe I'll just get rid of this whatever writing I have done here. Discard. Okay, so is my slides visible? Hello?
Yes, sir. Yes, sir.
Achha. Okay. So the point which we wanted to appreciate here is so whenever we are having the enclosure, in the enclosure, the net radiative heat transfer is not a straightforward thing. Okay. See here, this refractory wall, even though the net radiation from this refractory wall is 0, but still when we are calculating the heat transfer from the heat source 1 to heat source heat sink 2, it is not straightforward. This complicated part is coming into the picture, isn't it? Can you see the point? Correct. It's not just the shape factor A12. It's not just the multiplication of shape factor A12 here, A12 into A1. If I write in this case, whenever I am having the enclosure, in general, where we do the mistake in this, very often we write the expression for such cases as what? We write A1 F12 sigma T1 raised to power 4 minus T2 raised to power 4. This is what we write, isn't it? But this is not correct in this case because we are having the enclosure where this third surface is also participating, and because of that, instead of using a very simplified expression like this, we are getting a complicated expression. So this additional factor is coming into the picture. The additional factor in the sense this A1 is common, but this additional factor is coming into the picture. Is it clear to everyone? Hello?
Yes, sir.
So small differences are there, but you have to pay a little bit more attention when you have to use what expression. Okay. 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 So now let's. Okay. So far we have. Is there any question?
So the fourth wall wasn't doing anything.
I'm still not able to hear you out clearly.
The fourth wall wasn't participating in anything.
So first, what you are saying, the wall 1 is not participating.
Fourth wall.
There is no fourth wall. This refractory is surrounding. Okay, so if you look at from the top, how it looks from the top. Okay, maybe I'll just. I understood your question. From the top, if you look at the top view will be. Top view of this entire thing will be circular. Is it clear? It will be circular. So this refractory wall is surrounded everywhere. That's what it is. Okay.
Okay.
Okay. Okay. So let's look at slightly, more complicated situation. Okay, so we will be now try to derive the expression for the enclosure with n surfaces. Okay, and all n surfaces are radiating heat transfer with each other. Unlike the earlier case where this particular wall, even though it was radiating heat transfer, radiating heat to surface 2 and 3, but net radiation was 0. But unlike that, we will be looking at a generalized case now. So again, consider two black bodies 1 and 2 of surfaces A1 and A2, temperatures being T1 and T2, and their respective emissive powers are EB1 and EB2 respectively. Okay, so now the net radiative heat transfer, the rate at which the radiation emitted by body 1 and intercepted by body 2 will be given by what? A1 EB1 F12. Similarly, the rate at which the radiation emitted by body 2 is intercepted and absorbed by body 1 will be given by what? A2 corresponding shape factor F21 into EB2. Isn't it? And net radiative heat transfer between these two bodies will be what? Difference between these two, isn't it? So that's what we have put it here. Correct. But in this equation, this A1 F12 and this A2 F21, this we can relate with each other. So A1 F12 is same as A2 F21, isn't it? So we can just write A2 F21 as A1 F12, and if you write that, what we are going to get? We are going to get this equation. So this is only when we are having only two surfaces. This is true only when we are having only two surfaces. Correct. But let's say if we are having n surfaces, so the net radiative heat loss by the surface I because of its radiation interaction with all n surfaces including itself will be given by this equation. So summation, this equation is summed over all n surfaces including itself, is given as AI Fij sigma Ti raised to the power 4 minus Tj raised to the power 4. Is it clear? So its radiation with respect to itself will become automatically 0 because in that case Ti and Tj will be same. So that we can, that will be automatically taken care. That's why even though we are taking this summation from 1 to n, it doesn't matter. We have not put this I is not equals to j. This condition we have not put. It is not required, isn't it? Even when I equals to j, this will be automatically 0. Is it clear to everyone? Hello? Is it clear to everyone or not clear? So you may ask the question, why we are not getting a complicated expression here? So we are not getting the complicated equation here because in this case we have, we have considered a special case where we are considering that this refractory wall, corresponding to this refractory wall, the net radiative heat transfer is 0 for this refractory wall. That's what we are considering. Okay, so that's why we are getting slightly complicated equation here. But unlike that, in this case, we are not assuming that. Is it clear?
Sir, if the surface is concave in shape, then Qi will not be 0.
If the surface is
Concave in shape.
Concave in this shape, still Qi will be 0 with respect to itself. You are saying Fij might be different. Fij will be not non-zero, but what will be temperatures?
Oh yes, sir. Temperatures will be same.
So then it will be 0, na? This temperature difference will be 0, right?
Yes, sir.
Okay. Okay. So far we were only looking at black bodies, and as I said that we will extend it to a real bodies. Okay. So we are doing it stepwise manner. So we are saying that let's extend whatever the analysis we have done for a black bodies to a gray bodies. Why gray bodies? Because gray bodies, so gray bodies are what? The gray bodies are the bodies for which the emissivity and absorptivity are independent of the wavelength, isn't it? And why we are calling it as a gray? Because this particular property is similar to the black body. But why we are still calling it as a gray? Because these are between the real surface and the black bodies. So in the real surfaces, you can see that the absorptivity and emissivity are less than 1, and these are also dependent on the wavelength. But unlike that, in a gray bodies, absorptivity and emissivity are less than 1, but these are independent of the wavelength. Okay. So gray bodies are in between the real surfaces and the black surfaces. So if you look at many real surfaces, these behave like a gray bodies. Many real surfaces behave like a gray body. So that's why we are looking at the gray bodies. Real bodies, accounting the real bodies is very difficult. Why very difficult? Because this absorptivity, emissivity, all these are dependent on temperature and wavelength, and therefore accounting this complicated behavior is not very easy. So very often people use what? People use the gray bodies because that is slightly more closer to the real bodies, and they use the analysis of the real bodies to apply on the gray bodies to apply on the real bodies, assuming that the emissivity and absorptivity will not vary with wavelength. Is it clear? Is it clear? Hello? So you will see that even for the gray bodies, how the complications are coming in. It's not straightforward. Okay. Is it clear to you what I'm trying to say? At least the perspective is clear.
Yes, sir.
Okay. So there is some definitions. So the first definition is diffused gray. So diffused gray surface is a surface if its spectral emissivity E lambda, epsilon lambda, and absorptivity alpha lambda are independent of angle of incidence or angle of emission. So these are called as diffused gray surfaces. Okay. So again, many real surfaces have the characteristic close to the diffused gray surfaces. So that's why we are, trying to account this diffuse gray surfaces in the analysis. Okay. Then there are two important definitions, irradiation and radiosity. These definitions are important because these definitions are come into the picture when we are looking at the gray bodies or the real bodies. Because in the black bodies, what happens? In the black bodies, whatever the in the black bodies, emissivity is 1. That means emissivity is 1 means whatever the incident radiations are falling on the black bodies, these are completely absorbed. So absorptivity is 1 and the emissivity is also 1. So my analysis becomes very simple. But in case of the real bodies or a gray bodies, whatever the incident radiations are there on the real bodies or a gray bodies, not everything is going to get absorbed. That is the first complication, isn't it? Because my absorptivity is not 1. Again, the emissivity is not 1. So that means whatever the radiant energy emitted by a real body, you will have to multiply the emissivity there, isn't it? Correct. So some complications come when we are looking at the gray bodies and the real bodies, and these complications, in order to account that, these two definitions are there, irradiation and radiosity. So what is irradiation? Irradiation is defined as total radiation that hits a surface per unit area per unit time, and it is denoted by a capital G. So it is nothing but the total radiation from all sources that hits the surface per unit area per unit time. What is radiosity? Radiosity is the total radiation that leaves a surface, and this part which is written in the bracket is extremely important. The total radiation that leaves a surface by way of emission or reflection, both are accounted per unit area per unit time, is called as a radiosity. So you can see that if the radiations are incident on the surface, part of that will be reflected, part of that will be absorbed, and again because of the temperature of the surface there will be emission. So this emission plus reflection, total of that will be called as radiosity. Is it clear? So black body, if you look at the black body, black body does not reflect any radiation, therefore rho is 0. In that case, radiosity J is same as emissive power. But this is not same for gray surfaces or a real surfaces. For a real surfaces, some radiation will be because of some emission, radiation coming out from the surface. Some of that will be because of reflection, some of that will be because of emission, isn't it? So both the factors will be there in gray and the real surfaces, but in a black body, the radiosity is same as the emissive power. Is it clear to everyone? Does it make sense?
Yes,
Hello?
sir.
So small difference is there, radiosity and emissive power. There is a small difference, but that difference is very important. The difference is radiosity also accounts the reflection. Radiosity also accounts the reflection, and this becomes important when we are looking at the gray surface or a real surface. In case of black body, it doesn't matter because in a black body reflection is 0. It doesn't matter. But in a real surface or a gray surface, reflection is very important. And this reflection is also accounted in addition to the emission in the radiosity. So this definition, radiosity and irradiation, these are more, becomes more important when we are looking at gray body or the real bodies. Is it clear to everyone? Hello? Does it make sense to everyone? No answer from anyone. Is it becoming too much, guys?
No, sir, clear.
Achha. Okay. So you all might be thinking that why so much syllabus we are covering or something. Is it the question? So why we are covering everything? Because so I am trying to cover only the syllabus which is there in the GATE examination. So that is what you all are expected to study. So I am not digressing beyond that. Okay. All right. Can we move ahead?
Yes, sir.
So some complicated mathematics is there, but we will try to, do it. Okay. So what we are trying to do here is, so far we were looking at the radiation exchange between the black bodies, isn't it? That's what we have seen so far. A very nice expression we have obtained, a very nice expression like this, isn't it? Shape factor multiplied by area into sigma ti raised to the power 4 minus tj raised to the power 4, isn't it? So nice expressions we have obtained when we are looking at only the black bodies. But now we are trying to extend this analysis to a gray bodies. So in gray bodies, in addition to emission, the reflection is also coming into the picture. So some more complications are going to come in our analysis. Do you all agree? Does it make sense to everyone? Okay. So let's consider. Okay, so let's consider a diffuse gray body. So radiosity of a diffuse gray body can be related to a irradiation it receives, isn't it? So irradiation it receives, because whatever the irradiation a diffuse gray body is going to receive, part of that it is going to get reflected, isn't it? That's why the irradiation is also going to impact on radiosity. Okay, so let's assume that the EB is nothing but capital EB is nothing but the emissive power of a black body at the same temperature. So I am trying to do the analysis for the gray bodies, but what I'm trying to assume here is if I use a black body at the same temperature, what emissive power I'm going to get. So if my gray body is at, let's say, temperature T, but instead of this gray body, if I use a black body, what will be the emissive power? So that is given as EB. Okay, and this EB multiplied by emissivity, will be the amount of radiation emitted by a real or a gray body, isn't it? Do you agree with me? So this EB is nothing but the emissive power at the same temperature, correct? Hello? Yes. हाँ जी बताइए. नहीं मैडम अभी नहीं चाहिए. आई एम इन द क्लास. सॉरी. Okay, so all right. Okay, so emissive power of a gray body we can obtain that by multiplying the emissivity to the emissive power of a black body. Remember, black body is used as a basis to calculate the emissivity of emissive power of the real or a gray body, isn't it? If you multiply the emissivity to the emissive power of a black body at the same temperature, this word same temperature is very important, then I get the emissive power of a gray body. So are you all able to follow what I'm saying here? This first expression, is it clear to everyone?
Yes,
Hello?
sir.
Okay. Now there is another factor. Another factor is what? Whatever the irradiation, whatever the G, irradiation is denoted by what? Irradiation is denoted by G, and radiosity is denoted by J, capital J. So whatever the G or the irradiation I am receiving, only part of that will be reflected. And part of how much will be reflected, that depends on what? Reflectivity. So G multiplied by rho, which is nothing but the reflectivity, is going to give me the radiation reflected by the gray body. Do you all agree? Yes or no?
Yes, sir.
So this emission, whatever the emission we have obtained and whatever the reflection we are getting, the addition of both these will give me a radiosity J. Radiosity is nothing but the total radiation coming out from the surface by means of emission as well as reflection, isn't it? So this summation of both these factors is going to give me the radiosity J. Does it make sense to everyone? Correct. Now in this case we are assuming that only the reflection and absorption is taking place. There is no transmission. There is no transmissivity of the body. So transmissivity tau is 0. So in that case, alpha plus rho will be equals to 1, isn't it? Remember, that is what we have seen initially. Tau plus alpha plus rho is equals to 1. So fraction of radiation transmitted, fraction of radiation reflected, and fraction of radiation absorbed, that summation is going to be 1. That's what we have seen earlier, isn't it? Since transmissivity is 0, we can write this rho as 1 minus alpha, isn't it? And from Kirchhoff's law, we can say that the absorptivity is same as the emissivity when the bodies are in equilibrium with the surrounding. So 1 minus alpha can be represented as 1 minus epsilon, isn't it? So this rho can be replaced by 1 minus epsilon, isn't it? So my expression of the radiosity becomes J is given as epsilon EB plus 1 minus epsilon G. Do you all able to follow what I'm doing? Till equation number 24. Is it clear? Does it make sense to everyone? Hello?
Sir, how is the body in thermal equilibrium with the surroundings?
Okay, so what we are assuming here? What we are assuming is, okay, if you look at this body. So this body is receiving the radiation. This body is receiving the irradiation. This body is also, the radiosity is coming out from the body, isn't it? And because of that, the temperature here is increases or decreases, and eventually this body is going to reach to a fixed temperature where you are receiving a certain amount of irradiation, and you are also radiating a certain amount of radiosity, but temperature does not change. So that particular condition is the equilibrium condition. Is that the question you are asking?
Yes, sir.
Does it make sense whatever I said?
Yes, sir.
Okay. Okay. So at that condition, we can write down this 1 minus alpha is 1 minus epsilon. Is it clear? Does it make sense?
Yes, sir.
Okay. So now let's simplify. Let's simplify this expression. So, okay. So if A is the surface area of the body, capital A is the surface area of the body, the net rate of loss of radiant energy from the unit area of the surface is given by what? So net radiant loss, if I'm saying net radiation loss, net radiant energy loss is what? Radiant loss will be by two factors, either by reflection as well as either by emission, isn't it? Correct? So that will be given by what? Whatever I am receiving irradiation minus radiosity, isn't it? Remember, net loss word I have used, the net rate of the loss of radiant energy. So how much radiant energy I am receiving? I am receiving the radiant energy as
Irradiation. Yes.
G I am receiving, isn't it? G I am receiving, isn't it?
Yes.
And how much is given out?
J.
Okay, so J minus G is the loss. That's why this word loss is used. Okay, so J minus G is a loss. Correct? Does it make sense? Now in this case, okay, so in this case, this J we have already calculated. So J is nothing but what is epsilon EB plus 1 minus epsilon G, that we can put it in this equation. So if we put it in this equation, what we get is epsilon EB minus epsilon G. That's what we get. This epsilon we can take it common. So it becomes epsilon B minus G. That is nothing but the net radiant loss from the surface. Okay. Now, okay, let's simplify further. So in this case, so radiosity is given by what? Radiosity J is given by what? Radiosity J is given by this equation. Just a minute. Okay. Okay, so radiosity, this radiosity J we can calculate. Radiosity J from this equation of this radiosity, this G, which is nothing but the irradiation. This irradiation I can calculate. So J, this equation number 24, if you look at J minus epsilon into EB divided by 1 minus epsilon will give me a capital G, isn't it? So that is what we have obtained here. Okay. Now in this particular equation, this equation, if I put it in this original equation, so epsilon EB, this is the first term, minus epsilon G, this G, if I put it by this equation, I get this, isn't it? And if I further simplify, after simplification, what we get is epsilon B minus J divided by 1 minus epsilon by epsilon. So this particular equation gives me what is the net rate of radiant heat energy loss from a surface per unit area. Okay, now again, this particular equation can be represented in terms of a circuit diagram. So here you can see epsilon B minus J, that can be represented as a potential difference, and the resistance can be represented by 1 minus epsilon by epsilon. Okay, is it clear to everyone? So net radiant heat loss from the surface can be obtained by this equation 25, which is dependent on emissive power, which is dependent on radiosity, and it also depends on the emissivity of the surface. Is it clear? So we will continue from this point. So this is only for one surface, but let's say if you are having the enclosure of multiple surfaces, how this particular expression is going to vary, those complications we will see in the next class. Is it clear to everyone? Hello?
Yes, sir.
So we stop here, and from this point onward we will continue in the next class. Clear? Is it clear to everyone? Hello?
Next class is on Thursday.
So I don't think we have a class on Thursday, is it? Do we have? Thursday is 17. So okay, so no class will be there on Thursday. Okay, no class will be there on Thursday, and also we will not have a tutorial in this week. This Thursday class we will make up later on. Is it clear to everyone? Hello?
Yes, sir.
So we will not have a class on Thursday and no tutorial in this week. Both this tutorial and class we will make up later on after 21st. So we will have a quiz on 21st, but let me check whether I am able to get a timing 9:30 to 10:30 for a big classroom or not. So I will convey that to all of you by email today. Is it okay to everyone? Syllabus for the quiz will be whatever we have covered till today. Is it clear?
The quiz will be of same type like that what was
No,
conducted.
quiz will be like a offline examination which we conduct. So what you all have to bring in your classroom is either a book or a printout of class notes which I have given. Nothing else will be allowed. So this everything which I am covering in my slide is present in the book by BK Datta. So either you bring that book itself or you bring the the printout of whatever I have given you. No laptop will be allowed. So this will be examination like a offline examination, of course open book examination, but not open internet. No, open internet is not allowed. Only open book and open notes is there. Is it clear to everyone?
Sir, can we bring
means that-
calculator?
Calculator you bring, yes, you bring calculator, and I will give you a offline answer script where you have to write the answers. So this will be a proper offline examination. Is it clear to everyone?
Total subjective like we do in tutorial.
Correct.
One question, then solving it.
Correct. Yes. So marking will be a step marking. It will not be a final answer type of thing. That's what all of you have, conveyed in the this midterm feedback. Okay. So I am trying to follow whatever you have said. Okay. Is it okay?
So the syllabus is from post
Syllabus
minor,
will be whatever we have covered till date
from post
from class
minor.
1.
Okay, sir.
Hello. Excuse me, sir.
Please go ahead.
Sir, can we bring our handwritten notes?
No. So why you require a handwritten notes?
Like
Only
formula
a
sheet
class
or
notes
something.
is sufficient, isn't it?
Sir, like formula sheet or something.
So everything is there, self-sufficient. It is self-sufficient. Book is self-sufficient, and even all my notes are self-sufficient. All the formulas are there,
Okay, sir.
isn't it? All right. So we stop here, and we will continue. Let's meet on the quiz day. Okay. All right.
Thank you, sir.
Thank you.